Hey, welcome everybody. Thank you for coming. It's very exciting. So welcome to the fourth annual Wellner lecture. John and Vera Wellner are here with us this year. Great. Not all of you know this, but John is actually a graduate of the University of Idaho a little while ago, not too many few years. And then in mathematics, and then went on to get his PhD in statistics at the University of Washington, where he later returned, spent a good most of his career, and he's currently emeritus at the University of Washington. But what I understand, it's mostly just professor and less emeritus. Just nothing like nobody told him he's emeritus yet. He's still regular professor. So. Our speaker this year is Dr. Susan Murphy. Very excited to have her. She is the Mallinckrodt Professor of Statistics and also of Computer Science at Harvard University. She's also the Radcliffe Alumnae Professor at the Radcliffe Institute at Harvard University. She is a member of the National Academy of Science and the National Academy of Medicine. She was awarded the MacArthur Fellowship for her work in this area in 2013. Now my memory is now exhausted. Fellow of the College of Problems in Drug Dependence, past president of the Institute of Mathematical Statistics and also the Bernoulli Society, and also past editor of the Annals of Statistics. So Susan, thank you very much for coming out to talk with us today.
Yeah, thanks so much. So, so as you can well imagine, it's a big honor to be able to give the 2022 John A. Wellner lecture. I've known John for a long time. I met him when I just got out of grad school, and he's been a great role model. He was has always been a great role model for me. And what was even more important, at a very early time, John was a supporter of my career. And this is really big. You'll see what I mean. After you get your PhD, if you find someone who supports you as you develop your career, it just makes all the difference in the world. And so I really appreciate this, John, so very much. And he introduced me to Vera. I mean, what can I say? What we do in our lab is we work on in digital health. And in particular, what we do is we develop online algorithms that run either in the cloud. Normally, it's partially on the cloud and partially on some device. And here you see a picture of an app. So in this case, Oralytics, some of the code's on the app and some of the code is in the cloud. And normally, there's some sort of wearable that's collecting sensor data. In this case, it's a Bluetooth-enabled toothbrush. And I'm really excited to talk to you about this project because this project is something I've been striving to for many, many years. And this is the closest I think I've come to what I really want to achieve. And that's a setting in which you have some real problem that you're going to solve in real life. And you end up solving a rather theoretical problem in order to be able to solve that real problem. And this has always been quite difficult for me to try and get to that point. And I'll give you some indication of how we're doing that here. So I'm very fortunate. I have a number of collaborators. Kelly and Anna are PhD students. Billy Nahumshani, she's a quantitative psychologist. Vivek and Lucas Janssen, he's a statistician as well. And then there's an entire software engineering team that's connected to this. Vivek is an oral surgeon, and this entire study is going to go on in Southern California. And he is the person that recruits individuals and so on. Okay, so I'm going to talk to you about Oralytics. So Oralytics, the goal of Oralytics is to develop an autonomous oral health coach. And this is for people who are disadvantaged in a variety of ways. All of the individuals that are going to be recruited are people who get dental care at a number of public dental health sites in Southern California. And the trial is it's gonna go in winter 2023. Actually, I got an email today. We're gonna start running the pilots, the early studies to make sure the technology's good in January, and then the trial will start soon thereafter. And there'll be around 75 individuals in this trial. And it involves an app on their smartphone and then a Bluetooth-enabled toothbrush. So both the app collects a variety of data. You get enormous amounts of data about each individual coming in every single day. And there's so what happens is in these types of settings, these are sequential decision-making problems. So if, in classical applied math, you have this whole area of control theory. Well, this is modern control theory. It's control in a very different setting. So you're trying to control this intervention so that it really helps these individuals. And so what happens is there's an algorithm that you build. It's called a reinforcement learning algorithm, and it determines the kinds of whether to send a message to the individual, and occasionally what kind of message as well. I'll talk to you a little bit about that shortly. We're the algorithm developers, and these algorithms are heavily statistical. Okay, it's very interesting as a statistician. This whole field was born in biostatistics in the last century. And then all of us in statistics, this is the bandit algorithm, we all walked off, and people in engineering and in computer science picked it up. And now, and you can really tell we've been absent because a lot of the statistical problems have just been completely overlooked. It's quite interesting. Okay, so the setup is, this will be a 70-day study. Each person, of course, they usually brush 2 times a day. So the times at which a decision regarding sending a suggestion or not occurs 2 times a day. The state, that is the information one has in order to determine whether it's worthwhile to send a message, is the time of the day, morning, evening, whether or not it's weekend, weekday, how much they've been engaged in the app. All of these apps have many different intervention components, and the algorithm is only going to be controlling one of the intervention components. So you track how much they use the other components. Also how much they brushed the prior day. The action, that is the intervention here, or the treatment, we're going to focus on, our RL algorithm will focus on whether or not to send an engagement message. You see an example on the right-hand side. But when it does send an engagement message, it may send one of 3 different types. And the individual never gets a message that looks the same, okay? So it's, in actuality, there's 3 buckets of types of messages. And the buckets are large buckets. So the person message, all of these messages come out of behavioral economics. They're intended to help people stay engaged enough so they can achieve their goals of learning how to brush their teeth better in this particular case. The reward, so what's a reward here? A reward is the reward for the algorithm, not for the individual, okay? So when I say reward, I mean reward for the algorithm that determines whether or not to send a suggestion. And it's going to be the quality of the brushing that the person exhibits. So we reward the algorithm if that brushing quality is higher. And before, on the prior slide, I think I said something about micro-randomization is going to be done by the RL algorithm, just to give you a feeling for this. So you see 4 boxes here at the top. These are the different types of, again, they all come out of behavioral economics, and then there's the option of not. Our algorithm, again, will only choose between sending a message versus not sending a message. And then if one is chosen, then one of the 3 get selected. And the way it goes is every day, so this is in the morning, the algorithm does a randomization to one of these, the outcome is observed as well as the state of the individual. Then in the evening, the algorithm does a randomization to one of these, and then the outcome is observed as well as the state of the individual, and then the blah, 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 and so on. And now what the algorithm is intended to do is it's intended to bias these randomizations. So if sending a suggestion, say when someone has not been very well engaged with the app, is better than not sending a suggestion, it will increase the probability of sending a suggestion when the person is less engaged with the app. So this randomization is not, it's not like 1/4, 1/4, 1/4. It's not like that. It's getting biased according to the data that's coming in. So in these kinds of studies, and this is a classical setting where really having statisticians involved is critical. So in these types of studies, there's two objectives and they compete. And one is within the study on each individual, you want the algorithm to figure out when that person is most responsive and increase the chance of sending a suggestion then. And if they're less responsive, don't bother the person. And the reason, if you've ever downloaded an app on your phone, you'll know exactly why I say don't bother the person if possible, because it's very aggravating to constantly get notifications. So that's the within study learning. Essentially, one can say you want to personalize the delivery of these actions, these messages to the individual. Then there's the between study learning. So your digital interventions, that's a world in which everything is changing very rapidly. You don't just roll these things out and then forget about them. You're constantly having to learn. And so you have both that within study learning, but you have to have between study learning. And in the between study learning, that often has to do with causal inference. I'll give you some examples here. So within study learning, one deploys either bandit or other types of decision-making algorithms that attempt to bias those randomization probabilities in favor of the better performing suggestion. But between study learning, as I said, it's mainly causal inference. There's a whole variety. You normally have large teams of investigators. You can't pre-specify the variety of types of statistical or a data analytic, machine learning type algorithms they're going to want to run. But here's some examples. You might be interested in whether these messages have a differential impact on how engaged the person is with other parts of the intervention, other intervention components. You might be interested in whether that impact depends on whether it's a weekend or a weekday and so on. All of this helps you decide. Maybe you need some different types of messages in the next round. Maybe you need to observe different kinds of data and so on. These are the kind of questions you might ask in a between study. Again, these are two competing objectives. So there's some challenges. The within study learning is this between study learning is something statistics for decades we've been really good at. But this within study learning, this is quite difficult. And it's particularly problematic here because this is going to be a 70-day study. Each individual only has 2 opportunities per day. That means there's 140 decision points. That is almost no time to learn about that individual, particularly given the noise in this setting. It's one of the smallest number of decision times studies that we've worked on. And so it's extremely concerning. Because of this, we know that the algorithm that we develop, it's going to learn slowly. And if it learns slowly, it's not going to bias these randomizations in a way that's most effective for individuals. Lost my place. So what are we going to do? There's a whole bunch of things we do to try and speed up learning, and I'm only going to focus about one because I want to get to the real topic of this talk. But the one thing I'm going to talk about today is that the algorithm we're building is going to pool individuals autonomously in real time to bias those randomizations. So, for example, you might see that on average, in the morning, on the weekends, it's just not worth bothering people. There's too much going on in their lives. And what this does is, if you're a statistician, you'll be familiar with this. You trade bias and variance. People are not the same, right? So you're going to get some bias because people are not the same, but you reduce the variance enormously. So in the end, the randomization probabilities personalize more effectively because of the trade-off between bias and variance. So we really want to do this, and we've been wanting to do this for some time in our studies. This is something we really want to do, but there's some big problems when the algorithm pulls data in real time as the study goes on, and I'll talk to you about this. And this is what's held us up until this year. So we have to, it is absolutely critical with these types of big, these big teams, is you have to enable the collaborative team and further individuals that come along later to conduct a whole variety of data analyses, these causal inference analyses, what's called off-policy learning, and so on. And this work, the work I'm going to talk to you about today, is all about enabling that. Because if we don't enable that, if we don't manage this, we cannot pool data in this algorithm. It just can't happen. And everybody's sort of waiting on, anyway. Okay, so I'm going to talk, so this pooling of data across individuals to determine the probability of delivering a message which is personalized to the person. This is called adaptive sampling. And this is a big area right now. In industry, a lot of the ads that you're delivered on the web, that's adaptive sampling. They're using bandit algorithms. And there's enormous interest in how do you use adaptively sampled data to do between study inference. So I just want to explain how this happens here. So the way this study will start is you can see each row is a different individual, and you recruit these individuals. They're all independent because they're sampled from these high-risk clinics in Southern California. So from that population, they're sampled. They start off in the first, remember, so A here, A is binary, 1, send a suggestion, 0. Otherwise, S is the individual's current state, time of day, whether or not they're engaging with the app, and so on. And then R is the their brushing quality. So R occurs after the action is determined. So in this first round, what happens is you might randomize, say, with probability 1/2. Send a suggestion with probability 1/2, don't send a suggestion with probability 1/2. Okay, now you have this is all independent. One user from another, they don't know each other, they've never met each other, you just randomize. Then the algorithm, the RL algorithm, what it does is it takes all of your individuals, it takes all of their data, and it pools their data to form what I'll call a policy. And this is a mapping, this function, what it does is it inputs the next state of the individual's next state and outputs whether to send a suggestion. And it's often indexed by some set of parameters. So the way these RL algorithms work from our point of view is that they have two elements. One is some sort of learning procedure, like often it's Bayesian, a lot of times online it's deep learning, whatever. And so this beta parameter could be quite high dimensional. In our problems, it's not, but so different methods produce parameters which index this policy. And the policy takes the state and outputs a probability of sending a suggestion. So all of that data is pooled. You create the first policy. That's what the algorithm does. And then you take that policy, and on person 1, you input their current state. The policy then gives you a probability for choosing A = 1 or 0. Second person, you take that policy, it inputs present state, it gives you a probability, and so on and so forth. Right? Then again, the algorithm takes that data. Now it has 2 tuples for every single individual in this simplified setting, and it produces an updated policy. Again, this updated policy is going to input the state at time 3 and give you a probability for selecting send a suggestion or not. So what have we done here? what we've done is we brought a bunch of independent individuals. That's the beginning. Then we apply this pooling of data in reinforcement learning, and we end up with dependent people. Why are they dependent? They're dependent because this person's action is determined by pi, and that was partially determined by, so user one's action, treatment, is determined by pi, and that's partially determined by how well user three responded. So you induce this very artificial dependence between these individuals, even though they've never met each other. You end up with these dependent data trajectories. You have a trajectory at the end of the study, you have a trajectory for each individual, and they're dependent between individuals. The problem now is that if you use classical data analyses, which were for the most part intended for independent units of data, individuals, you mess up, uncertainty quantification goes down the tube. Yeah.
Sorry to interrupt. I'm just a little confused. Is it only tracking if they got a message at all, or does it also care what message they got?
Yeah, that's part of the state. So the state, well, you're totally right. It's a good question. The state the state is massive.
Okay.
Just massive. Yeah. So we know what message they got last time, and whether they got it very many times in the past.
Thank you.
So I just want to, so the whole talk is about this issue, this problem of this artificial dependence induced by this algorithm, adaptive sampling. That's what people call that. So let's just talk about between study learning. So if you think of the ith individual has this trajectory that's made up of state action reward, state action reward, state action reward, this long trajectory. In our case, capital T is 140, which is not very large in this world. Again, this is why we want to pool. And classical statistical methods, when they see long trajectories, one per user, and they allow very flexible, I mean, they don't even often make an assumption on the dependence within a user, within an individual across time. They'll call this longitudinal data. And so in a longitudinal data setting, the treatments, say the treatments that I got last week might even influence how I respond today. I'm sick of them, for example. That would be a perfect way you would get that. So you allow this very general dependence between tuples within an individual in longitudinal data. And that's traditionally one uses longitudinal data analyses to do between study data analysis. However, this classical approach, this classical way of analyzing data, it assumes the individuals, their data is independent. Those trajectories are independent from one individual to the next. And that's not the case here. It's patently not the case. And this violates that. So again, just to push home why this is problematic, I just want to show you this little graph on the right-hand side. So here's the setting where where it's just in simulation, but it's to illustrate the idea. The algorithm was just a two-arm bandit. And at the end, one just wanted to estimate the treatment effect at the end. So it's a difference between means. It's nothing special here. And here's a histogram of those treatment effects. The true treatment effect, the true data generating process had a treatment effect of 0. And here's all the different histogram of all the different means. If you ran this study over and over again, this is in a simulation environment. And a difference between means should look like a normal distribution. The distribution of difference between means should look like bell-shaped. And it's patently not. The red line is the normal distribution. It's clearly non-normal. And like if you were going to do a significance test, like hypothesis test at 0.05, you get a doubled type 1 error rate. So it's a big problem. the violation of a standard approaches. So you not only get problems that you have, it's spread out, but it's not even normal. It's not a normal distribution. Okay, so what I'm going to do on the next slide is I'm going to give you the assumption we're going to make on the algorithm. Now, it's not really an assumption because we developed the algorithm. So we're going to ensure our algorithm satisfies this assumption, right? That's the privilege of being the person who's, right? And I'll talk to you about why it makes sense to make this assumption. Okay, so the primary condition on this algorithm that's being run during the study to determine the probabilities with which a person gets a suggestion or not, is that that probability concentrates. And so here, the way what we're saying is that whatever parameters you're learning as part of the RL algorithm, they go to some constant, maybe in probability, maybe almost surely. That's not important. But what's important is that they converge. Now, so let me talk to you a little bit about this. So most RL algorithms and bandit algorithms that are used like by Google and Facebook and so on, they're what's called regret minimizing algorithms. And these types of algorithms, there's no concentration. You can't guarantee concentration. What happens is the betas, they never settle down. And in fact, this sort of looks like a p-value. In some settings, it actually converges in distribution to uniformity. I mean, there's no concentration. And this is because they prioritize within-person learning within study learning over between study learning. They say, forget about between study learning. I don't care. All I'm going to do is go for within study learning. And that's fine. I mean, if you're Facebook or something, maybe that's fine. You can throw away you run your one time and you throw away the data and you're done. But you can't do this in these health settings. The data is way too expensive to collect. So what we're going to assume is it does concentrate. Our algorithms the algorithms we run satisfy this property. And indeed, if one is developing, remember, this is an area of control. So if one is developing the right kind of controller, or RL algorithm in my language, for a non-stationary setting, this in fact is what happens. So it makes sense if you're worried you have a non-stationary setting anyway. So what happens is if you're in a world in which you're able to make this assumption because you're the designer, which we are, the usual type of approximations that statisticians use to produce confidence intervals, measures of confidence, they still hold. That is, that you can approximate, say, the difference of two sample means by a normal distribution and derive a confidence interval. And it works pretty well. And that's what happens. The minute you get this concentration, we still have that. But the dependence between the individuals means you have more variation than you actually think you have. And this makes sense because now let's go to sample surveys. In sample surveys, I don't know how many of you guys have had sample survey. Anyway, in sample surveys, the way you collect, you survey or sample your people is you often sample them in clusters. And what happens is this produces a dependence. And here we have a similar sort of dependence. So you never have as much information as you think. That's what increases the encoding of lack of information or reduced information, that it gets encoded through the variance. That's what we're talking about here. This is where the trade-off between within study learning and between study learning occurs. If you go for regret minimization, you give up completely on, you can't even do, only under very restrictive settings can you do between study learning. If you now don't try to minimize regret, but you put some constraints, you don't minimize regret, but you gain that you can do inference afterwards. You just have to adjust the standard errors for the dependence. Okay, so I'm going to talk about this this turns out to be a big problem. How are you going to adjust for this dependence? First of all, even realizing that this kind of assumption would get you part of the way there was a big issue. And then, so does anybody have any questions before I go on? Okay, no questions. Okay, so here I'm going to, what I'm going to do is we're going to talk about some traditional classical statistics. A regular applied person would use if they're analyzing data from a clinical trial. Okay, we're not talking about this problem. We're talking about a regular guy who's going to analyze data. And you're going to see how things go down the tubes. Okay, so in a classical world, theta is your treatment effect. It's what you really want to estimate after the study's over. I mean, this is what happens with all the drugs that you and I get to take, all of pharmaceutical, this is the dominant way in which a lot of decisions in our society are made. So you want to conduct inference about this treatment effect, theta star, and the way you estimate theta star from data is you solve what's called an estimating equation. And I'm going to show you an example from least squares on the next slide. But this estimating function here, it inputs the data and it's indexed by theta. You set it equal and you sum over the number of individuals in your study. You have n individuals, we have 75 approximately. You set that equal to 0 and you solve for theta. That's what you do. And that gives you theta hat. That's the way, these are called Z-estimators. And they're the dominant, almost all of statistical methods can be put into this framework. So an example of an estimating function is least squares. What you see here is the first derivative of the least squares equation. It's the first derivative with respect to theta 0 and theta 1. It has the those two factors, theta 0 and theta 1, that one wants to estimate. Theta 1, of course, is primary interest here because that's the treatment effect. Remember, A is an indicator, send a suggestion versus not. So you would like to estimate theta if you had the infinite amount of data. So that's what this, you want the true theta 1 and theta star. They solve this expectation, which is an expectation assuming essentially infinite amount of data. Of course, you don't have infinite amount of data. You only have n individuals. And so what you do is you average it over the n individuals and you solve for theta 0 and theta 1 and you get your estimators. This is like standard statistics. I don't know. I'm like in a first semester stat class, I think you would do this sort of thing. Okay, so what's the problem with for us? We have to figure out how our estimator theta hat, that's the treatment, our estimator of the treatment effect, how its variance, its uncertainty increases because we did this online pooling. We have to get that straight. So we have to mathematize in some way how this theta hat, this estimator of the treatment effect, is implicitly a function of how the data was collected. And the data was collected with these parameters that come out of our reinforcement learning algorithm. They were learned by the reinforcement learning algorithm. We have to figure out that implicit function. Theta hat is a function of all those parameters. Now, in classical statistics, you would say this is not very special because we do this sort of thing all the time in classical statistics. I mean, when I say classical statistics, I'm talking about, like 1960 or I'm sure in 1960 they knew how to do this. I'm not going to swear to that, but I'm pretty sure. Okay, so this is how you would do it in classical statistics. You got to mathematize this. So what you do is you recognize that your estimating function, that's this function. In our case, it was least squares, remember the least squares equation. It's not only a function of theta, that's the treatment effect that we want to estimate, it's also a function of all those other parameters, the way that, in our case, it's the way the data was collected. And this type of estimator, this comes up like just all over the place that one sees this. And what do you do now to figure out how theta hat is implicitly a function of all those parameters those beta hats, what do? You do Taylor series, right? Because Taylor series is how you propagate uncertainty. So what I do is I take this equation and I take the derivative of both sides with respect to this large vector. This is a pretty large vector of parameters. I take I take the derivative with respect to all those beta hats on this side. I just get 0. I take the derivative of this with respect to the beta hats. First, theta, of course, is defined as a function of beta hats because theta hat it solves this equation. So I take the derivative of theta with respect to all the beta hats. I just write that like that. And then I actually see how to take the derivative here. And then I solve for theta hat, the derivative of theta hat as a function of all the beta hats. That's the whole game. And this is how you propagate. This is the underlying conceptual idea for propagating uncertainty about the beta, the way the data was collected, to estimating treatment effects. It's the way we do it. And we use this first order Taylor series, first order derivative. This is great. It's worked for us for decades. It doesn't work here. It just doesn't work. Because if you look at our setting, those betas that were used to determine by the RL algorithm, that were used to determine the randomization probabilities, they're not in our estimating function. I mean, you don't see them anywhere. We have our data. This is our state action reward for each individual. It goes in there. We have our treatment effect we want to estimate, using least squares here. You don't see any beta. Where's beta here? Where's beta? It's gone. It's totally just gone. And that's because the only way beta comes about is it's used to decide which data to observe. It's not explicitly in this estimating function. It's determining what DI is. This is an enormous conundrum. So how am I going to differentiate both sides with respect to beta? I mean, I don't know how to do it. I mean, how am I going to do this? This is a disaster. I mean, it seems like it's a disaster. It seemed to us to be a disaster. And for years, okay, so I've actually done multiple studies where I ran RL algorithms and I refused to pool the data. And the algorithms didn't learn as fast as they could because I didn't know how to deal with this problem. I just didn't know. How am I going to differentiate this and see beta come out? I don't know how I'm going to do that. Finally, we had the breakthrough this year. It's just so exciting for me. You know how it is if you're trying to prove something and you finally get it, but it took you like months. Well, okay. And it's just so obvious. So, okay, wait. So let's think about derivatives. When you take a derivative, it's not like you take a derivative at one point. It's like you need some local, generally, you need some local smoothness, right? And then it's like you take different paths and you take the derivative from all those different paths. That's how you get a derivative, with some local smoothness. So we have to figure out the local smoothness in theta hat as a function of these guys. What do? So we use this trick. This is simply for proofs, just like all of great math. It has nothing to do with reality. It's totally a proof. I mean, I just love it. It just made me so happy. So anyway, let me just tell you why. Okay, so what we did was we take our estimate. Remember, this is the least squares equation here, the derivative of the least squares. So we took it and we weighed it in the proof. And the denominator corresponds to the way in which we actually sampled the data. We sampled the data with beta hats because the RL algorithm was learning in the process among people to decide what actions to select. And so it's like a Bernoulli draw. This is a Bernoulli distribution right here, probability mass function. And then I just put the same thing in the numerator, but now I don't have hats because there's no learning. These are just parameters that I'm going to use for differentiation purposes. Now, what is theta hat? If you change your estimating function by putting this this product in the front of it, what's theta hat? Well, theta hat is just where you put in place of these betas here, you put the actual beta hat's output by the RL algorithm. But in that case, this ratio reduces to 1. So at the point that you want to take the derivative, that weight, that ratio reduces to 1. But as soon as you get locally in a neighborhood, it's not 1 anymore. Because the betas are slightly different from the beta hats. These are radon-nicotine derivatives, by the way. We collected the data under this distribution, and we locally around it, we want to think about that data under a different set of betas. So now what you do is you differentiate both sides with respect to these betas, these guys, the numerators. Turns out the denominator does not contribute to the increased variance. You just differentiate with respect to the betas. You have a derivative term here, a derivative term here. Of course, theta is it's implicit derivative of theta with respect to all the betas. It's great now. Now you can go through the proof and derive the increased variance. I just want to point out that actual data analyses, they don't have a weight. This is totally a technique to derive the standard errors, the variances, so that we can get confidence intervals and propagate uncertainty. Okay, so I'm gonna give you the theorem, because you have to give a theorem, because that's what you're supposed to do. So I'm gonna give you the theorem. I won't give you all the assumptions. This is a classical kind of theorem you see in statistics. I'm saying that the distribution of theta hat, remember theta hat is like an estimated treatment effect. As the amount of data, the number of individuals in gets larger and larger, you can approximate the distribution of theta hat. It ends up being centered at the true treatment effect. And it has some, the way it's centered is according to a normal distribution, a symmetric distribution. It has a certain type of variance. This is a classical kind of variance that occurs in this setting. At least it looks classical. The outside parts are the first derivative of the estimating function. So the second derivative, the least squares. And then the inside part is looks like this. This is a product. And what's the term due to this this sampling, the adaptive sampling? It's this second term. You get this adjustment that comes about just because of the derivative of theta with respect to all the betas. That's where the increased variance comes through. And I wrote F here. This is actually a linear function of this vector. It involves matrices, but I didn't, it takes too much space and I wouldn't have been able to put it on the slide. So I just wrote, but it's linear, and you can find all of this in this archive paper. So it's great. It's totally good. So now we can start to think about running that trial. Of course, we have a lot more to do, but I'm going to show you some, I'm just going to give you some intuition about this using a simulation environment, just to be able to make a couple of points. So let's say in reality, our reward, the ground truth linear model, it's a linear, let's say the ground truth is indeed a linear model for the reward. In our case, in Oralytics, this is like the brushing effect, efficiency. It's a function of the current, whether or not that person got a message, and then some past history of the person. We're going to have a correlated error terms in these linear models, so there's correlation across time. And we're going to allow the effects of these past actions to exponentially decay in this simulation environment. But they still are, you do have the effect of prior actions onto the future. And we're going to use a really toy algorithm. This toy RL algorithm will use linear regression at each time to form the beta hats, and then it'll randomize to send a suggestion or not based on, this is called Boltzmann exploration. You take this ratio, this is a number now between 0 and 1, and we actually clip it below by 0.1 and 0.9. The reason why this is one of the many things we do to manage between study inference and within study learning. Now, our this algorithm, this very simplistic algorithm, it's completely messed up. It's it only thinks the current state is the prior brushing efficacy from the last time and just an indicator. So it's not according to the ground truth. And in general, you can't expect the algorithm to use a model that's in accordance with the ground truth. That's okay. Now we're ready. You run the simplistic algorithm, you end up with longitudinal data. And we use a classical traditional biostat method called generalized estimating equations. That's what GEE means, generalized estimating equation. It's just least squares. But you least squares where you pretend as if there's no correlation within a person. And then you adjust for that in your standard errors. And our least squares analysis, well, again, it's not going to have the correct state. It's going to just use the prior current action and some interactions, and that's it. Oh, and our state is the last time how well they brush their teeth. And it's going to use our adaptive sandwich estimator to get the variance. So how does this all do? So what we're going to do is we're going to compare it to the usual way a statistician would do this. So here's a case where, and the way I set this problem up was our model, the model that we're using for between study inference is not the correct ground truth model. And you see if we use a usual sandwich estimator and I want a 95% confidence interval for my treatment effect, I only have 64% confidence. So this is really bad. You can see how things really go down the tubes if you don't adjust. And our estimator does somewhat better, 87%. If you increase the sample size, it doesn't really help if you use the usual sandwich estimator because that's not the problem. It's not a matter of not enough data. But our method gets much closer to 95%. Now, we have to, okay, so I'm going to talk to you. Let me just finish. I have to give you there's multiple messages. Now, if our model is correct, if the model that generates the data is the same as the data analysis model, which is the same as the reinforcement learning algorithm, so everybody gets it right. The algorithm gets it right, our data analyses get it right, everybody gets it right, then actually you don't need this estimator. The confidence intervals are great, which is great. So if everybody gets it right, the confidence intervals are good. So that's the first message. If everybody gets it right, things are great. But if you have any kind of misspecification, it goes down the tubes. The second message, and this is well known in statistics with these generalized estimating equations, is you have to have a small sample correction when you have a smaller samples. And that's what we're working on now in order to run the Oralytics study. And there's standard ways. This is not going to involve me to invent new math, some new theoretical tool. Okay, so this is my last slide. So what's the next steps? Right now, we're developing a package using R. We will then give this package to the biostatisticians, biostat teams on these. So we're the computer science teams on these things. It's very weird to be at the computer science team. But anyway, that's what we are. We're going to develop this R package. It goes to the biostat team because they have all these analyses they want to run. And it's going to have to include a small sample correction. And also, if you're used to trials, the whole time I've been talking, you should have been very suspicious because I pretended like everyone got recruited on the same day. And we all know that's completely fallacious. And so this correction, this will have to adjust for the incremental recruitment. And then, so right now we're doing this because we're writing the design paper. If you're familiar with clinical trials, this is a very high stakes environment. So what happens is we write a design paper and we have to register the trial. And in this design paper and in this registration, it goes on clinicaltrials.gov, we have to precisely state all the algorithms that are being run and the primary data analyses. So that's what's going. Everything is waiting for us to finish bullet point 1 so that can go and get registered so we can do the trial. And the trial is intended to start end of January. That's my last slide. Thank you. Oh, did the camera follow you?
I think it's on you.
Yes.
That was fun talk. Thanks for.
Yeah.
I learned a lot. So you considered kind of the two extreme cases, right? Where you have all individuals are individuals and we treat them separately, or you pool everybody
Yes.
together.
Willy-nilly.
I mean, you could envision, right? Intermediate cases, maybe you group people by age,
Yes.
or there's morning people and night people,
Yes.
or even an adaptive version of that, like where you treat people by age, but then you see, oh, that person acts like a young person, so
And you
change.
move them to another cluster.
Yeah, or
I'm
you
totally with
you
you.
have different clusters and maybe the
Yeah.
number of clusters changes as you get more information.
Yeah, I'm totally with you. And
Yeah.
all of that was on hold until this was in the standard error thing. Everything was waiting because you cannot run one of these trials. They cost enormous amounts of money. If you can't allow people to analyze the data, you know, you're dead. So right now, because of this, now I have a postdoc who's from operations research. She's totally into machine learning and everything. And so she's developing a method where you can recluster people. You start them in clusters and then people can move out of the cluster and you do the poll. Okay, that's one. And then we have another study. So hers, we don't have a study yet. We're just developing the methods. She's much more of a theoretician. And if it all turns out, maybe it'll go in real life. But then we have another study that this is actually going to go. This is for kids that have been, they're in bad trouble. They're in a lot of trouble because they've been smoking pot a whole lot. Like 4 or 5 times a day, and it's starting to interfere with their jobs. And so there's a whole intervention package, but we're going to have one part of that, one of the components. And there, my plan is to use some sort of it's called meta learning, using random effects. So to smoothly pool. So in some states, most people will act similarly. In other states, people will act very differently. And to understand that when people act more similarly and when people act more differently, to learn that, that's what we plan to do there. I just want to say all of these algorithms, these oral algorithms that we run, they're always Bayesian, and we usually have informative priors. And the reason why, and the informative priors are built on prior data on similar individuals. And the prior, if you're a computational point of view kind of person, the prior is just a warm start because these are online optimization algorithms. And the prior is just intended to get you in a neighborhood of the optimum so that you can learn more. Yeah. But I am so like this is what we've been wanting to do for quite some time, and I just couldn't do it. And actually, I'll tell you one more thing. I know of 2 studies where people actually pooled. They wrote up that they didn't tell the funding agencies. They wrote up the study, and it got even in one case, it got published in a very prominent medical journal. Clearly, no one was watching. And the p-values are like, for the treatment effect, for a small sample, are like 0.00001 or something. This does not happen in this world. So anybody who knows this world knows you can't get p-values of that size. So, but no one was watching. No one was watching the thing. So we're trying to fix all of this. This is a problem, like AI is so popular, and a lot of times the individuals who develop AI, this is not the case now, but at the time of that trial, the individuals who were developing AI algorithms, they didn't really understand the negative consequences that these algorithms could have. There was this cowboy kind of attitude. And now, of course, it's very much changed. I mean, there's enormous emphasis in truth in advertising now, but at that time there was much less. And so the computer scientist that was involved, that developed it, he's a friend of mine. He says, he just didn't care how they analyzed it. That's their problem, how they got to analyze the data. Of course, now you know what I mean. But at that time, he just didn't understand. Yeah.
I was curious about the reward for the
Yeah,
algorithm.
the reward
and-
for the algorithm.
Right, and sort of how the time lapse between the message and
Mhm.
when that reward.
It's within like an hour. It's within about an hour period of time.
So and that's just set, it's not something that you.
No, it's
adjust
that
to the individual.
well, it's not set in the sense that we don't control the individual, like so each person's decision times are according to their own life.
Yeah.
So yours and mine might be different. And then they may brush their teeth right after they get a suggestion. They may wait 30 minutes. If they have small children, they may end up waiting a little bit of time, like 45 minutes or an hour. So we don't control that. That's just an
Oh, I
attribute.
just
But
meant
we-
how long before, maybe they waited 2 hours and it doesn't count anymore. That's what I was like.
Yeah, there's
a period of
concern-
time where it no longer
yeah.
is seen as a reward by the algorithm.
Right, that's a state variable. So the state variable is, one of the state variables for the next state is the time at which a message is sent and the time at which they brush their teeth. That's a state variable for the next time. It can't be a state variable for this time because it's post-treatment, right? But it indicates something about that person in that context. You know what I mean? Because like someone, you can imagine someone who the algorithm may not know that they have young children in the morning. They may always have these delays, mainly due for family settings.
Is it similar? I've seen some papers on like nudges. right?
Yeah, these
nudges
might
or
be,
something.
but nudges are not PC, okay? They're used in the economics community, but in the health community, you really don't want to use that word. So that's why I didn't use the word, because I've been fussed at now so many times. But in the behavioral economics literature, they're called nudges. So that's the right word for behavioral. Yeah. So what were we gonna say?
Oh, I'm just curious about, whether some of these other studies that I've seen, are they all gonna have intrinsically these types of problems that you're talking about?
Oh yeah, all over the place. There's all kinds of problems going on, and because this is a new field and a lot of it it's not like, okay, I have a friend, I'm a mentor on like with these young behavioral scientists, and I'm a mentor on this one particular behavioral scientist who works in depression, digital interventions for depression. And she did this big literature review because she knew that people were not really using the app. People would stop using the app within the 8 weeks they were supposed to use it while they were being treated clinically. And she just thought this must be a big problem. So she went and she reviewed the literature of all the digital interventions that were reported in the clinical literature. And for the most part, no one said anything about people not using the intervention. And then she found 10 papers out of all the papers where they mentioned it, and there's gross non-adherent, gross dropout, because the interventions are not as engaging as they need to be, right? Or the people don't feel like, they don't perceive they're gaining benefit. And this is quite disturbing to her because most of these trials are being reported and no one's mentioning that, 50% of the people stopped using the app after 2 weeks or whatever, you know what I mean? So there's a lot of problems in this field, but people are genuinely, there's a lot of good faith now. People, it's maturing really nicely in the sense that people are really trying to make an effort to do more truth in advertising. Yeah.
So I was wondering, are the treatment effects estimated during the trial? Do they?
The algorithm estimates treatment effects on its reward. It estimates treatment effect, that's those betas.
Uh-huh.
Those are estimated treatment effects by the algorithm on its reward. And it uses those estimated treatment effects, or their posterior distribution in my case, because it's a Bayesian algorithm, to determine the randomization probabilities.
Oh, I thought theta was the treatment effect. So I was actually.
Theta could be a treatment effect, say on engagement or some other. So the reward is the algorithm's reward.
Uh-huh.
There's always these other kinds of outcomes that people care about. And theta is the treatment effect on those other, it could be a treatment effect on the reward, but it's often treatment effects on other things too. Like how long do people stay engaged with the algorithm? You might want to know, if they've gotten a lot of messages of type A, do they tend to be engaged with the algorithm longer than not?
So does theta inform the policy?
Theta can be used to decide, so it's normally a vector, and normally they do and they usually have some causal inference. It's not just theta, they do a whole variety of analyses, and they'll discover that like one message just does not seem to be resonating in any particular state. So they may some new developments that they read, and they'll replace that type of message with a different type of message for the next trial. Or there'll be a better toothbrush they'll hear about, and they'll say, oh, it has similar sensor readings, and we want to replace it because of the noise level in the sensor readings we have in this trial. So all kinds of human in the loop decisions get made between studies, but they're informed by the data analytics, the theta hats, and the confidence sets associated with those theta hats. Yeah, so like Oralytics is actually a series of studies. This won't be the last one. As soon as that trial's over, we're going to have to do all those between study analyses, and then we go to the next trial of Oralytics because we're going to continue to re-engineer. And there's also a lot of qualitative studies that go on where you interview participants and you ask them about perceptions of burden, perceptions of benefit. So it's not, I'm not involved with that, right? But it's part of that team. Yeah.
The main goal of this project is to teach these patients how to
Brush their teeth
brush their
well.
teeth, or to remind them, or to learn or to investigate how their algorithm can affect their behavior.
The main goal, the scientific goal, the dental health goal is to help teach people how to brush their teeth properly. To get them to brush their teeth and to have them brush their teeth properly. It turns out this is much more complicated than I thought. Okay, I didn't understand this before. Now I'm a very good brusher of teeth. But before, it turns out I was not so hot. But that's the goal of this entire series of studies, is to get to the point where people can learn well. And these are pretty disadvantaged people, so their dental health is not that good.
So this work's really very new, but I know you've worked a lot in the past with micro-randomization.
Yeah, I've been doing a lot of this.
So now that you've got this done, do you have any temptation to kind of go back to some of the other things that you researched in terms of digital interventions?
Oh, yeah, like
The
we're
exercise and things like
oh,
that?
yeah, right. So we just wrote a grant in cardiovascular disease. And I'm pretty excited about that one, but I really don't know how we're gonna pull it off. Don't review my grant, please. But in that one, the behavioral science has a whole, okay, so how do people encode causal theories? In the behavioral and health sciences, they draw directed acyclic graphs. And the information in these graphs it's qualitative information. This is not mechanism, this is not physics, okay? So the information in those graphs is the absence of the arrows. They don't really know how to mathematize the connection between two nodes in the graph, but they will speculate that an arrow is not there. And what happens is there's these theories about dynamic theory. Okay, so dynamic theories of how we change our behavior and how we maintain behavior change. Turns out okay, I gotta proselytize just a second. Like most of the morbidity and cost and health in our society today is heavily impacted by our behaviors. Healthy eating, exercise, managing your stress, getting enough sleep. I mean, most of the cost in our society is centered around these big, it's actually 5, but I've forgotten what one of the 5 is. But anyway, okay, so this is cardiovascular disease. Anyway, So they have theories about how, and the behavioral science has only started at the health science is only in the very beginnings of a theory for how we change our behavior and how we maintain a behavior change. And so they have these ideas of like in physical activity, like this grant has this, is you want people to all of a sudden start thinking of themselves as a physically active person. So like a lot of people, they exercise because they know, you should exercise. It's a good thing to do, blah, 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 whatever. But they don't think of themselves as physically active. And the problem is if you're the kind of person who doesn't think of yourself as physically active, if you sprain your ankle, you're much more likely to not get back on track. So the chances of you, if you have anything happen to you, the weather changes, it gets really bad, everything goes down the tubes. And so in that grant, they have these directed acyclic graphs, and they postulate how these slowly evolving views of self-identity as a physically active person change. And one of my tasks is to think, how do we use that directed acyclic graph to construct a reward for an algorithm that'll be effective? How do we, I don't know, you know what I mean? That's part of my job. And so how do I do causal RL? RL that's informed by DAGs, directed acyclic graphs. I mean, that's really exciting. I have no idea what I'm doing, but it's exciting, right? So that'll be really interesting. I'm pretty excited about that. Oh, and the other thing we're doing, okay, I'll tell you about one more thing that I'm really excited about. So for years, I've been wanting, in addiction and in mental health, in addiction and mental health, it turns out our social network is really important. And in fact, in addiction and in severe mental health, we destroy our social network. So, and of course, if you have severe mental illness or a severe addiction, it's not like we give you a digital intervention that's going to cure you. This is only one of the interventions that you're getting, okay? No one's making this up, right? So what I've been wanting to do for a long time is to have RL algorithms that operate on the social network of the individual as well as on the individual, because we know that the kind of support a person gets when they're trying to change their behaviors, we know, not me, but is very important to achieving behavior change. So what we're doing is we're thinking about how can we develop algorithms that collaborate with each other. One algorithm will be trying to increase the strength of edges in the social network, move them towards a more positive valence with higher strength. And the other algorithm will be targeting that individual in terms of whatever, like medication adherence. And the problem I'm thinking of is medication adherence. This problem occurs all over the place. So I'm pretty excited about that. So the one that we already have funds for, these are kids that had leukemia, and now they're in recovery. And their social network is just a dyad. It's their care partner and the child. And this is a really bad situation because the parent is in this awful situation of having to try and make sure the child takes this awful take-home chemotherapy for like 2 years in order to not relapse. And so the relationship is fraught with problems. And are there things that we can do using behavioral economics and others to try and help that relationship? They have some really interesting ideas. Anyway, so we want to try and improve the dyadic relationship and improve the child's ability to adhere. Those are the two big projects. Those are my two big next projects that we're going towards. That's cool. It's very exciting. Yeah, it's very exciting. And I really, like I said, I don't know what I'm doing. I'm just doing the best,
Now let's thank our speaker. So we have a reception over at the IRIC. Any questions? Everybody is welcome. If you don't know what it is, follow somebody, what's where they're going. And afterwards, some of you will randomly be instructed to brush your teeth.
It turns out, women in the US are much less likely to brush their teeth than men. Huh, I'm glad to tell you that. Yeah, it's probably caregiving. Women are really bad. No, women. Yeah. Men are much.
Surprising.
It's
To me,
not-
that's,
it's always the women that are more caregiving, not in.
yeah, you're supposed to do it right all the time. Guys.
No, the guys are good, the men, the women are.
Live.
Yes.
Oh, I did, yeah, fell off.
A sample of more than 75.
It was like
Oh,
the
yeah, these
randomizer
are
did it.
big, big.
There was an intervention that gave me.
Recording is instruction.
I think my wife would give me that intervention.
I don't know if we didn't stop recording.
Well,
don't know, but
as soon as we
Oh,
shut
no, it says
down.
recording.
We'll stop.
I have to ask one more quick one. 'Cause